is like what makes something an acid and a base. We're going to be labeling and classifying these things so you need to understand, well, what makes something an acid and what makes something a base. Now, officially, there's actually two definitions of acids and bases. They're kind of like just in the timeline of history. There's the first one that came out from a guy named Arrhenius, but then they kind of realized that his definition was like lacking. And so then later on, these two people, Bronsted and Lowry, came up with a more complete definition. So that's the definition we will use in this class. If you were introduced to acids and bases in junior high or elementary, they typically start with the Arrhenius definition because it's simpler. But once again, it's lacking. So the first thing we need to recognize here, though, is this idea of water. Okay? H plus is a significant particle when it comes to acids, and we'll get more to that here in a second. What we need to understand, though, is that all acids and bases are in aqueous solution, meaning they're always in water. It's not an acid or a base if it's not in water. Okay? And what happens is anytime H plus is in water, it turns into this. Does anyone remember from the packet what H3O plus is called?
Hydronium.
Good, Tyler. That's a name you should just know, because we're going to be like using it a lot, right? So you should know H3O plus is hydronium. Because of this relationship, chemists use H plus and H3O plus interchangeably. This is really what's in the water, but sometimes when we're lazy, we just call it H plus. But technically, H plus always becomes this. So as you go through today's lesson, we're going to be writing like two different reactions sometimes, just to show like the complete form with hydronium and then like the simple form. But recognize like they are one in the same.
What you said earlier, like all acids and bases are aqueous.
Yeah.
So is baking soda not actually a base? Have I been lied to?
Great question. It's not really a base until it dissolves. Once it becomes aqueous, then it can act as a base. But technically, until it dissolves, it's not really a base. In terms of like the behavior of it. Yeah, great connection there, Michael.
Is it possible to have H3O without water, like at all, like just a solid H3O?
Good question. Nope. When something has a charge, they don't exist outside of an aqueous system.
So if you were to like evaporate water with hydronium in it, the hydronium would also evaporate into nitrogen and oxygen. So
Yep, for sure. Yeah, good observation. All right, any other questions? Because we're going to be looking at both of these. Just recognize if I say this, it means this. Or if I say this, it means this. This is the true form. This is the lazy form, but they mean the same thing. You can pick what type of chemist you want. Okay? All right, so this idea of the hydrogen is what describes an acid and a base. By definition, an acid is a substance that donates what we call a proton. Now, proton is the nickname for H plus. Oh, that's a sticky marker. Right, so H plus is nickname a proton.
identifies a proton.
Why would H plus be nicknamed as a proton?
Because that's all it is.
Pretty much, right? There's probably neutrons, but if hydrogen loses its only electron, right, it's just a proton and then whatever neutrons it has as well, right? So that's why we call acids are proton donors, bases are proton acceptors. So when you're looking at a balanced equation, you want to be able to identify if something is an acid by comparing the left to the right and tracking this movement. So what I notice is on the left side of the arrow, the H is bonded to the Cl. But now on the right side of the arrow, the Cl is by itself, and the H2O has gained the extra H. So the way to kind of track it is you can show that the H is going from here to there. Notice that it's only the H. The electron stays behind, which is why it's Cl negative and H3O positive. So we would identify that HCl is an acid because it's donating its H.
So the only thing that makes it an acid is the fact that when reacting with water, it makes it H3O.
Correct.
So,
Yep.
wait,
Are there certain acids that are favorable in certain reactions because it has different products, like byproducts? Does this one have chlorine floating around after the reaction.
Yeah, yep, so some would be like more driven, if that's kind of what you're referencing, like more acidic or like better at being it than others would. And then what's interesting is in this case, our water is acting as a base because it is accepting pH. Now you're gonna find there's differences between acting as an acid and base versus actually being acidic or basic. Water is not acidic or basic as we'll learn, but it can act in either form.
So when we put acids on our hand, does that mean the acid is giving us a lot of protons? That way we melt when we have them.
That's part of the corrosion, yeah. This is extremely reactive, so this starts reacting like
So then bases kind of do the opposite thing where they take our protons and then.
kinda, yep. And
So could like an acid act as a base just because it's like a less strong acid than what it's reacted with?
for sure, so we'll learn, if I'm understanding your question, we'll learn that some substances are what we call amphoteric, and they can be an acid or base just depending on what they're with. They kind of are like, well, if you'll take it from me, you can have it, or if you want me to take yours, fine, I'll do that too.
There's a people pleaser.
Any other questions on identifying an acid versus a base?
Acids give and bases take.
Yeah, acids are donors, bases are receptors. Okay? Alright, before we talk about this, for some smiley faces, identifying these two equations, which one is the acid and which one is the base. You talk to your table buddy, let's see if you can fill that in. Ready, set, go. I'm gonna go grab one more chemical.
Well, except for that one. I just look over here to see which one's plus, which one's minus. Whichever one's plus is the base, whichever one's minus is the acid. Because if you take away a proton, right? And so it means that whatever negative gave away its proton, and whatever positive, you see the proton, because the proton is whatever it releases.
I don't know how much they like.
I don't think it's made, I guess, if there was metal.
I don't know.
Or like when
I saw like why is coffee's getting like
Are we ready? Okay, so in order to get this smiley face, you obviously have to label them both, right? Okay, 'cause they both can be acids or bases. Okay, so in this first one, you should have said that this is the acid and this is the base. Yeah, so one smiley face for that problem. Questions on this one? And then on this one, you should have said this is the base. And this is the acid. Questions on identifying acids and bases given a whole equation. Yeah.
So is the base just always a little bit more?
Like on the other side? Or like,
Like on this side, like it works in this case, but like.
no. Yeah, focus on the movement of the H. That this started as HNO2, but then on this side, the H is now gone, and we see that it was taken, right, so that kind of being able to draw the arrow of where the H goes. But that is an interesting observation based on these problems.
No, this say that for the products, we say that the one that is a negative is the acid, and when it's positive is a base, because if it's a positive, it means it received the,
Like in the matching pair of it?
yeah.
Yeah, that would always follow the transfer story. Now, with this being said, kind of going off what Izzy pointed out, the reason why Unit 7 is placed in equilibrium right before Unit 8 is that equilibrium plays a very big role when it comes to acids and bases. So we're going to be using equilibriums a lot again in this unit. So what happens is an interesting thing is that when you have an acid-base reaction that does an equilibrium, if we look at it in reverse, so now we're going from this side to this side, how could I label my NO2?
Would it be a base?
It could be labeled as a base because going from this side to this side, I now see the H is going back that way. So we have what is known as a conjugate base. I just abbreviate conjugate as a C. Okay? The conjugate base is the thing that gets created from the acid, but now going in reverse can act as a base. And then vice versa, this would be our conjugate acid.
Is that kind of like an equilibrium?
Yep. Is that like, if you just look at it in reverse, you have an acid and a base again. To kind of signify the sides, that's where the word conjugate is coming into play. Where the acid and base are the ones on the left, the conjugates are the one on the right. Okay? Now what's important to recognize though is that when a problem says, hey, identify the conjugate pair, okay, this is the conjugate pair. The pair is the relationship between the acid and the base that gets made, not acid to conjugate acid, right? Those things are not connected. Okay, try this one first, smiley face. Identify the conjugate acid and the conjugate base. Ready, go. Okay, everyone ready to check it? Okay, if you said this is the conjugate acid and this is the conjugate base, you can have another smile.
Only one?
Just don't worry, it's still early. Okay, questions on conjugate pairs? Okay, on a scale of 1 to 5, 5 being the most confident, how confident do you feel identifying acid, base, and conjugate pairs? So on a scale of 1 to 5, if the very first question on the quiz were to say, or the test were to say, identify the conjugate acid, base pair in this problem. Okay, perfect. All right, we're going to skip the next practice problems for time then, because it's just more practice with conjugates, since we all are 4 or 5s. And your POGL about conjugate acid base, if you haven't done it yet, has lots of practice for you. So when you do that, you'll get more practice as well. Okay, all right, flip your page over to that. Let's look at a really weird reaction. Okay. Water, as we've talked in other ways, is a very important compound. And the properties of it are really unique to the things that it can do. So scientists have figured out, as we saw in both those problems, that water can act as an acid, water can act as a base. And water actually does this with itself. So we have a reaction that is known as the autoionization of water. That one water molecule can collide with another water molecule, okay? And we'll say this one's acting as the acid. I mean, it doesn't really matter because they're both the same. This one is acting
mixture?
Yes.
Does that mean if you drink water, you're also drinking acid and base at the same time?
What about eco-friendly?
Yes.
Wait,
No,
if
so-
they cancel, does it mean that it's safe for you? Like, what if all of the water was divided into these two things? Would you dissolve or would you be fine?
Would you dissolve?
Oh.
So generally speaking, drinking hydronium and hydroxide would be very bad for your insides.
How bad?
At the same, what if
Like,
you mix it in a beaker for
Probe
like a couple
through your
minutes and then drink it?
esophagus. Back.
So cool.
So, like, what if you mix hydroxide and hydroxide?
So these things by themselves are very bad. Now, what is significant here is this. Okay? Jack, what did you say? Why is water okay for us to drink?
So little hydroxide.
This equilibrium is extremely reactive in favor. So the amount of hydronium and hydroxide I drink is very, 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 very small, right? Which is why it doesn't do much. So every 2 out of 1 billion particles are this. So every billion I drink,
How much water would I have to drink to start like destroying my insides?
you probably drown yourself before you got to that point. But, so that's why in the end, this process happens, but it's not like problematic for us, right? Go ahead, Steph.
Are all like reactions like do they all go back and forth or is it the same?
No, so not everything can be an equilibrium. Yeah, there are, we just came off our equilibrium unit, so it kind of feels that way, but there's a lot of reactions that are only one way.
Okay.
Yeah.
What if you added like,
Say what? This is equilibrium, yeah.
if you added a catalyst to the reactants, and then you went into like a tub full of like,
Fusion.
would you dissolve?
So theoretically, it is an equilibrium, so you could maybe try to disrupt it, right? Use Le Chatelier.
I don't know, if you added heat, like a lot of heat, and somehow contained
You
it.
just boil before
But
you
then you
dissolve.
might have other problems besides.
Like
You
God,
boil and then
this is all
dissolve.
theoretically, so if you somehow found a container that contained all the water, and also would keep it so it was liquid, so if you pressurize enough, it'd keep it liquid,
Okay.
and hit
That's called an Instapot.
really hot. Like really hot.
Instapot, yep.
But like maybe more than instant.
Okay, okay.
Potentially we could just separate the two, like, right?
Theoretically, yes.
Theoretically.
Let's theoretically try it. Who has a superheated instant pot?
Because of the heat. Yeah, why
You
it's
gotta just
hot.
be cooking
But we'll talk about why it still is actually.
your instant pot will heat your food for you.
Yes, Annika.
So, is there like a really small chance that maybe right before you drink a lot of water, all of the acid things like go like that, and then you can drink
Kinda
the
like
water
watching
and just
Totally,
dissolve
like-
it?
I guess, I mean, probability, right? Like,
Temperature today, son. I
Is that
learned
kind
beer
of like we
water.
talked about how you could slam the table and your hand could go through it?
yeah, like, there's that probability. You know, well, if the probability were to line up that the molecules at that time happen to be.
And then you also do it at the same time, like in order
Okay, focus back up front here, everybody. Focus back up front. Okay, so with this idea, we are now, because now that we're looking at equilibriums, we still have equilibrium constants. So in the acid-base unit, equilibrium constants are a big part of it. What I want you to though is keep it the same. Just because we're like learning about it again in a different way, don't change it. So in general, what is an equilibrium constant? What is a capital K?
Product of reactants.
Good, it's the ratio of the products compared to the reactants, right? So if I wanted to write the equilibrium constant for water, which we signify as Kw, the W there is just because it's a special reaction, but it's still the same thing. So if that's my equation, what goes on top? Products. So I'd have OH negative and H3O plus. Now, what do we not include in equilibrium expressions though?
water.
Solids and liquids.
your liquids or your solids, so we don't include the reactant. So Kw just equals this relationship of hydroxide to hydronium, and it always equals 1 times 10 to the negative 14 at 25 degrees, because once again, K's are temperature dependent. 25 degrees, by the way, is considered standard temperature for reactions. So when they say this reaction is done under standard conditions,
How much is 25 in,
it's about 75.
So just room temperature basically.
So kind of like room temperature,
a
maybe a
little
little
hotter,
warm, but
a
yeah.
little uncomfortable room temperature?
So this ratio is what's going to lead us into the pH scale of acids and bases. That when these two things are equal, that's when we classify a substance as neutral.
What if
So
they're
in
slightly equal?
pure water, they have to be perfectly equal to be said as neutral. If the hydronium or the H plus is more than the hydroxide, now the solution has become acidic.
Space.
And then on the reverse side, right?
No reverse, that's also acidic.
Okay. By the way, I have some equations over here. We'll learn more about the other ones. But here's this first one. These are on all the purple ones are on your formula sheet. So as we learn them today, recognize you don't need to memorize them, but we just need to know how to use them. So this Kw equation is on our formula sheet. Okay. Now, we could simply just look at these to identify something as acid or base, right? So we can just say, well, how much hydronium is in there? If it's more than hydroxide, then we know it's an acid. For whatever reason, scientists said, well, sometimes concentrations are like tricky to look at because they can be numbers like 1 times 10 to the negative 7 or 2.5 times 10 to the negative 12, right? They're often large or very small, I should say, exponent numbers. So scientists then developed this pH scale to translate a concentration into a nice clean 0 through 14 number instead. But all the pH scale is telling us is it's just helping us understand the amount of this ratio. Okay, we're going to skip this practice problem for now and we'll come right back to it. But I want to come to this equation first. Okay, so to calculate the pH of a solution, you simply take the negative log of how much hydronium is floating around in there.
And it's always the common log, right?
Yes, log base 10. Now, we got introduced to logs last time, so hopefully if you haven't learned them in math, you're not too frightened by them. Once again, in this class, there's just a few things you need to understand about them, but mostly your calculator is going to do the work, because you'll just type it in there. Once again, this just simply takes whatever the concentration is and flips it to a much cleaner number, right? It would take 1 times 10 to the negative 6 and change it to just 6. But that's why the pH doesn't have a unit attached to it, because once it goes into pH, it's just a scale. Before it's in molarity, but now it's just, let's compare a scale.
So does that mean all acids and bases have the OH3O plus? Because when we measure with the little pieces of tapey thingy, whatever they're called, they have it. So does that mean all acids and bases have the H3O2?
Very good, yeah, they always have both.
Okay.
What makes it acidic or basic is when you have more of one than the other. So this is the same as our box before, but now let's write an answer in terms of the pH scale. So when these two things are equal, we said, what type of solution is it? Neutral. And the pH will equal 7. Nate?
So if you have like hydronium ions in a concentration above 1, wouldn't that make the pH negative?
Yes. So the pH scale looks 0 through 14, but isn't. It can get broken outside of that, as we'll see in a second. Good observation, Nate. Okay, if H plus is greater than, what type of solution is it? It's acidic, and the pH is less than 7. So the way the log works is it kind of flips it, where if you have a lot of this, you get a low pH. So that's kind of what understanding log is important to recognize, is that the bigger this is, the the smaller the pH will be. And then vice versa, if you have very little H plus, then the pH will get bigger than 7.
So technically it's kind of based on the concentration of the base, right? Because if there's a scale of 1, like it's a 1, it has a lot of H plus. But if we're doing a scale of 14, the base would be at a 1. And then if it gets to a 14, the base would be at a 14.
Yep, and then it's like inverse of each other. Yep. Okay, let's come back to this question really quick, and then we'll keep moving on. This is a very popular AP question I've seen, like every year on the final AP test. It changes, but the root of the question is the same. Like the numbers won't be the same, right? But what it's asking is. They love to ask it, because it's kind of a weird question. It says that the KW for water is now 3 times 10 to the negative 14 when we've increased the heat to 40, right? Because we know that the K changes the temperature. What is the pH of pure water now at 40 degrees? Okay, so the thing to recognize here is the KW value has changed. But what KW equals has not. Okay, so we still know that OH and H plus are going to equal this 3.0 times 10 to the negative 14. Right, the value has changed, but it doesn't change the setup. The other thing, and this is going to be a very common question throughout this entire unit. What does pH measure?
Acidity.
How much base is it?
Concentration.
The concentration of H plus or H3O plus, right? That's literally what the H in the pH stands for, is it's the power of the H, right? How much H plus is there? So whenever a problem says, what is the pH? My brain says, well, I need to know how much H plus there is, right? If I know how much this there is, then I can take the negative log of that to find the pH. Now, because this substance is water,
It's 7. I don't know.
it's not 7, but what's true about these two things because it's water?
They're equal.
They're still equal. So even though the KW has changed, it doesn't change the fact that these two things are equal. So I can change it to x squared equals, because I know they're going to be the same whatever they are. Which then allows me to square root it. So you get x equals, you square root both sides, 1.7 times 10 to the negative 7, I think is what we get. So then, we need to take the negative log of that number,
It is.
which you could type into the calculator, or by estimating, you know that it needs to be less than 7, because when you estimate it, you go to the power and it has to be lower than that, so I know it must be 6.8. Which if you type it in your calculator, you get that. But.
So hot water is not 7.
So when we heat the water up, it has now become a pH of 6.8. Acid.
Wait, does that mean you can cool water? No.
But now here's the question. Don't say anything out loud. Think to yourself, does that mean my water is more acidic? Shake your head. Give me a thumbs up if you think yes, it's more acidic, or thumbs down if not. So the pH is now 6.8. Has my water become more acidic? I like those of you that can't make up your mind. Every time I turn my head, you have a different answer. The correct answer is it's not. Nate, what do you think it?
Because you have an equal amount of hydronium and hydroxide, so it's not more acidic.
So what happens to the pH scale when you're not at standard temperature?
It's broken.
Yeah, you shift it, right? Or you break it. The
So
pH scale doesn't work.
at 40C, 6.8 is neutral.
Still our new neutral. Yep.
So I can drink hot water.
Yes. I mean, you probably shouldn't because it's hot. But in terms of the only way to disrupt it is you have to shift the amount of one compared to the other.
How much in Celsius is Fahrenheit? Like a 1 Celsius.
Oh, it's not an easy equation. It's like 5/9. I don't even know.
We just measure in Celsius all the time.
Because we're America. Yeah, Annika.
Well, so if like the KW or whatever is like, if the pH scale is measuring how much H plus ions there are, and like the more it has, like the more acidic it is, why isn't it flipped? Like why isn't it the more H plus the higher the scale?
It's because of how logs work, and because we're taking the negative. It's kind of the negative in front of the log. The negative log is what causes the scale to flip versus like normally a lot of H,
Yeah.
but then it gives you a small number. Does that make sense? So, okay. Any other questions with this idea of pH before we introduce you to some more equations? Okay, I forgot to tell you this one. This was on our last one. Oh, sorry, Tyler. Go ahead.
Well, I was just saying, if the last one H plus equals.
Oh, thank you. That's what I was going to cover. So plug in this right here. So if you ever need to do this reaction or this equation in reverse, let's say they give you the pH, but you want to know the H plus, then you use this equation, which if you're familiar with logs is just the inverse of a log. I wrote it in pink though because it's not on your formula sheet. Sorry, I think they just assumed you know it from math, but that's fine. But that's how you do it reverse. So. Okay. Any other questions so far?
Is everything else on the formula sheet?
Yeah, all the other purple ones are. So yeah, Benny.
Why do we only care about the H plus, not like the H minus?
Technically, you can find either, and that's what we're going to see here in a second as we look at the reverse. It's just for whatever reason, scientists said, well, let's just pick one scale to focus on, and so they picked H plus. But technically, you can describe all these things from the OH side of it, and there is something known as the POH scale. But it's just, to be, I guess, universal, they just picked, for whatever reason,
Oh,
H
is the
plus.
pH scale like the P and then the H is for H
H
plus
plus
ion?
is for each ion.
And that's why it's a weird capital?
Yep. Yeah, but you don't think like, in an alternative universe, they maybe exist on the POH scale, which is the same. Okay, this isn't on your notes, but I want to emphasize it here. You hopefully got it as a takeaway from the activity last time. But on the idea of logs, what you do need to understand is how big a difference. So when something has a pH of 6 versus the pH of 7, 10 times the difference because it's log base 10. So just keep that in mind. Don't be deceived by like, oh, it's only a, 7.2 versus 7.3. Like that's still a big difference on the pH scale. In terms of like your body, our blood has a very specific pH range. And if it just goes ever so slightly out of it, you go into blood acidosis, which is not a good
What is the
H plus?
7.3 something, 7.4 something.
Oh.
But it's like a very small range, like it doesn't.
So it can't have like perfect water.
Yeah, you don't want, no, we want that range. Our blood is slightly basic. Okay, let's try a few problems here just to get familiar with these equations. Once again, if you did all of POGO, you should have gotten lots of practice with them, but this is just trying to make sure we know how to use them. So,
I was supposed to submit those yesterday. I saw them on Facebook.
submit them today if you have it. So this one says calculate the concentration of H plus, and we're given OH minus. So this is similar to our water problem, just recognizing that as long as I have one of these, I can always find the other because they always equal this constant value, right? So if I know OH is 0.01, I don't know my H plus, but I do know it's going to equal this number. You can always find, right, algebra is a missing piece, so I just divide it by 0.01. We get H plus would equal 1 times 10 to the negative 12. So just recognize, once again, it's just kind of getting familiar with what you have available in your toolbox. So depending on what's given, you know what tool to use.
So this concentration is very basic. Because it's 12 pH.
Yep. Yeah, very good.
Could I look one of those like pH things to test how like acidic my water is?
We do that in general chemistry.
How acidic
You
is?
spit
Why
on it.
can't we do that? That's cooler than writing it down.
You want to lick a piece of paper?
Yes.
Yes.
And watch it change colors.
It's better than writing
Absolutely.
down why you think a piece of paper would do what it does.
I'll go get some pH strips in a second. You guys can all lick them.
Yeah.
And honestly, your saliva is somewhat dependent upon if you just ate something recently, that can change it momentarily. Okay. These types of problems, what I'd like you to do, in case you didn't do it last time, you do need to make sure you know how to use your calculator's log button. Because the calculator will do the work for you, but if you don't know how to use your log button or like where to find it, that's going to be problematic. So if you have your calculator, pull it out. And I want you to just practice typing this in just to make sure we know how to do it. Okay, try these two really quick on your calculator and see if you can get the right answer, just to make sure you don't type things in wrong. This one you should get 12. You don't even really need a calculator, but just once again, the whole point here is you don't want to know how to do all the work, but then you type it into your calculator wrong and get the wrong answer. Once again, most of the time it's pretty straightforward. You just type negative log, parentheses, the whole thing, close the parentheses. I don't remember what this one was. 5.25? I guess I didn't remember until I started saying it out loud. Anyone need help finding their log button or how to use it?
Yeah.
Once again, most are straightforward. A few calculators can be like backwards, so we just want to make sure you know how to use it. When you take statistics, you'll use commas. Your calculator can do you ever remember doing like problems, I don't even know math, what order you think. Have you ever learned about like, I have a bowl and it has like red and blue and white and green, and like what's the probability of like pulling out? So like your calculator can solve those problems for you. Like it has like an equation, but you like have to separate like 3, choose 2, and the comma's like what separates it. Yeah. That's what statistics in college taught me was, wow, my calculator can do a lot of stuff.
I know, I like this one. This is my best friend.
It does a lot more than what I realized it could do. I mean, it does a lot in calculus, but in statistics, there's like, it's all, you don't do anything by hand anymore. Okay, no question about typing in logs? Okay, last part of this, and then we'll get back to molecular side of things. Okay? Oh, I guess I forgot this one. So this is like an example of the reverse. So it's giving me the pH, and it wants you to find the H+. Yeah, apple juice is acidic. Most fruits are.
What's the pH of hydrochloric acid?
Are vegetables basic?
0? Is the pH of hydrochloric acid 0?
Stay tuned, because I have some hydrochloric acid right here, and we're going to add some indicator to it.
And we cannot drink hydrochloric acid.
So that's how you use the inverse of a log, is by just taking 10 to the power of it, which ends up being
4 times 10 to the negative 4.
Thanks, Michael. And then once we do come out of the pH scale, we are back in molarity.
So that's like what is an on the formula sheet, right?
Yes, so this one is not on your formula sheet. If eventually when you learn about logs, this is how you inverse a log. But if you haven't learned about logs yet, or log base 10. Okay? Okay, we're gonna add these equations now to your paper as well as other options in your toolbox. Okay? So put this equation in the top box up there. Maybe my slide's too high. So that very top box up there, right? POH equals. Look, the box is here. Right? No, there's not. Oh, well, the box disappeared. So next, above this box, draw a box and write this equation. So the POH equals the negative log of OH minus. And just to emphasize what Annika noticed earlier, the letter P is like a formula indicator of that when you put the letter P in front of something else, you're saying take the negative log of that P. The power of hydroxide, the power of hydronium, and then we have this thing known as pKw, so put that in this second box here. And just like before, that means we're taking the negative log of Kw. Now that feels like, what's the point of that? And it just gives us a really cool connection between our two pH scales. In that sense, the pKw equals 14. The pH of something plus the pOH of something will equal 14. So this is just what allows you to link the two scales together depending on what units you're in. And it's almost like you have an excess amount of equations, like you don't really need all of them, but some of them will make the process faster by using them than others would be. So, once again though, careful to recognize that we break it if we're not at 25 degrees Celsius. But every problem on the AP test, except for those water questions, will be at 25 degrees Celsius.
What's the P actually stand for?
It's like the power of is kind of like what it's referencing because log is like a 10 base system. That's like the best definition I found when I've researched what does the P and H stand for.
They just say, power of P.
Yeah. So, okay. Any other questions on the pH scale and the math of it? Okay, we're gonna take a minute break before we do our next part. So everybody stand up, take a quick stretch. Okay, get your blood flowing. Wake yourself up. What's interesting is like certain things don't react with acids, right? Because like obviously you have to have something to store the acid in, right? So, like glass. Oh, I mean, I guess if someone made something. Okay, sorry, I forgot 2 beakers. Let me let's write that.
I guess you need another.
What the heck? Okay. She brought it first.
Someone wrote something last period too.
There's a big shard in the middle. I'll be out. There's a big shard in the middle right there.
Oh, it is. Right there. Right there. In the middle. It's shiny. It's like you missed a spot.
Yeah, they're not like there's various levels of like glassware, and there's like some that's like pretty strong, like Pyrex, but this one's because you know.
It was her fault.
I guess. It was Lily's fault.
Yeah.
She used like her Harry Potter like
Exactly.
magic or something.
Exactly.
Okay, let me go grab one more beer.
We just scared them all.
Listen, I'll drink another beaker.
I swear.
I'll drop it.
It'd be really funny.
Can we just be like, alright, we're done for today? Okay, I'm just gonna do that one. Okay, so the next thing we want to look at here, everybody. So, foundational thing from our beginning takeaway, once again, is identifying what acids and bases do by behavior, and then the pH scale and what it measures. Okay, we're going to be continuing this pH discussion almost the entire unit. So just always remember that when I'm measuring the pH, it's measuring that amount of the hydronium that is floating around the solution. Now, in terms of lab practicality, there are a variety of ways in which you can measure pHs. We have a very official thing known as pH meters, which you guys will use, which is a device that you can stick straight in like a thermometer and it will read out a number. We have a lot of visual methods that are more colorful and fun, not as accurate, but a way to also indicate it, and they're known as different indicators. Now, there are thousands of indicators that exist in the world, and their purpose just depends on what you're trying to achieve. So what this image is showing you is it's showing you kind of the flip switch for that particular indicator. So if I was using the indicator methyl violet, that's the indicator's name, methyl violet flips at around a pH of 1. So anything less than 1 is yellow, but anything greater than 1 is violet. But it's important to recognize that 14 is violet, 6 is violet, so you only would use that indicator if you're wanting to see the flip switch.
So you have to use like a bunch of different notices if you really didn't have no idea what it was like.
Yes. Or that's where you can use the pH meter, or we have what is known as the universal indicator. So the universal indicator changes colors for every pH number.
That's what's on the piece of paper.
I would take this class again on pH paper.
Oh yeah, so well pH papers can also be simple ones, but they can also be universal. Yeah.
What's the pH of the pH?
Okay, so let's just see a comparison
I want to
here.
do that.
So this is a 0.1 molar hydrochloric acid. Okay. So we're gonna add acid to this first one. We're gonna add water to the second one.
What's the pH of pH paper?
I don't know, melt it down.
Yeah, wait, how would you even measure? You couldn't, right?
No, because it was liquid protons that would dissolve.
Yes. And then I'm gonna add sodium hydroxide, which is a base, to this one. We'll use our fourth
The
one in a
universe
second.
is the only one who knows.
Can we? Yeah, can we put the indicator on the pH paper?
Yeah, can we put
So
that?
we can like see.
Put the pH paper on the uranium whatever thing. Universal
You want to know the pH of this?
Yeah.
Well, what color is it?
Green. But what about the pH of the pH? Would it turn different color?
pH of the pH.
pH of the pH. Like we're getting into like
When I said like this, I'm making
I don't quite understand what you're asking, but I can do that if you
We
want.
just solved the paper.
Okay, so I'm gonna add some of this to each. So this was our acid.
That is
This
so
is our water.
That didn't change.
And then that's our base.
That's a pretty acidic water, it's like yellow.
What if you mix all of them in the yellow one?
Yeah, distilled water when it expires, because of the plastic, starts to become more acidic, which is why it has an expiration date. So it should have stayed green, but obviously my water is a little bit expired. But you can still see somewhat of the idea of the pH scale, right?
Mix the purple one, cause it's like weird.
That's so cool. How much is a bottle of that? Like, nice snaps.
Or the
What
red.
if you did a mass spectroscopy of the
Yeah, oh, there's a lot that goes on. Which makes sense because of all that. Mix
Can you pour the red into the purple?
Mix them.
momentarily. Momentarily, we'll get there.
Is the universal indicator edible?
No.
But if you want your stomach acid to turn red.
Hey. That would turn one thing very much, because
So-
our blood's slightly basic.
But
As we
hydrochloric acid
now
is what you
continue
use
talking about
also.
acids and bases, everybody, we now have, so we've learned about what's an acid and what's a base. We now have two different classifications of acids and bases, where we can say this is a strong acid, this is a weak acid, this is a strong base, this is a weak base. The first thing you need to separate is it has, the definition of strong and weak has nothing to do with the pH scale. Okay, the definition of it when I call something strong and call something weak is not about the pH scale. It's about what that substance does in solution. So there are 7 strong acids. If it's not one of these 7, then it's classified as weak. Eventually, I'll tell you when, but we are going to memorize these for, it just helps in problem solving to already know what they are. But let's focus on the last 2 where I didn't give you the reactions for them. What makes something a strong acid is that when it is in water, which they all are, it doesn't exist as a whole compound. It exists as separate ions. So perchloric acid here, so HClO4, write this one with me. If I could magic school bus into a beaker of perchloric acid, it wouldn't be this. What I would see in the beaker is it's separated apart. So strong acids, what makes them strong is their full, complete ionization. They don't exist together, they break apart, which then gives you...
So they dissolve in water and then mix? Or is it not
They-
like dissolving?
I'd say it's more ionizing, like it can already be dissolved like this, but ionizing meaning it breaks apart into
Once it's in an aqueous solution?
Yes.
Okay.
Okay.
That's weird.
So what makes something strong is its ability to completely ionize into its 2 components, okay? Now this is, I gave you both reactions up above. This is like the simple way of looking at it. Let's do the more complex way for sulfuric acid, just to see the difference, but it's the same idea. So this is the simple way of showing it ionizing. The more complicated way is saying this plus water, which once again, saying it's aqueous, water is there. But now we're gonna show it giving up its H. So it makes H3O plus and HSO4 minus. Keep in mind the definition of an acid is only giving up 1 H, by the way, not multiple that has multiple. Okay? Questions on these equations?
No, but I have a dumb question.
Would HSO4 minus also be an acid as well?
Very good, yeah. It's
So
not
they're
strong anymore, but it can do a second step reaction. Yeah. Good.
So is hot wrinkles kind of messed up when it's like plus on the wall?
Yes, so that rule only applies when it's not in solution. We have good connection of remembering. Normally, like H can exist by itself, but out the window because it's surrounded by water. So it's not really alone, I guess. So. Okay, any other questions on these? How we wrote them?
What were you saying about strong earlier?
So these 7 acids, okay, so hydrochloric, hydrobromic, hydroiodic, nitric, chloric, perchloric, and sulfuric, these are the only 7 that do this complete process.
That's why they're called strong?
Yep. And that's that's the definition of strong, is that complete ionization.
But do
Okay.
they like all have different like numbers with the H scale?
So, to answer your question, I'm going to ask you a question. So right here I have, where's my gun? So right here I have acetic acid, which is a weak acid. It's not one of our 7. Okay? I'm going to pour it in and we're going to add our indicator. So this was hydrochloric, a strong acid. This is a weak acid. Now what does pH measure again? Good, concentration of H+, right? So let's add our indicator to our weak acid and see the difference.
Still red. Oh, that's boring.
It's like
Right?
What's more
It's kind
like,
of the same. Yeah, it's the same.
It's a deeper red.
It's, I'd say it's a little more red, but it's really, really close. So what's going on there? If this one's weak and this one's strong,
I mean, it's
Maybe
reacting
it's
the same
the
way
same.
though.
but they have the same pH, what's going on at the molecular level?
maybe it's more reactive. Because it doesn't like.
Getting
No,
there.
it's not.
Michael?
The one on the left is doing the equilibrium dynamic shift thing.
Yes.
Then the right is just fully done.
So how are they at the same amount of H plus then? You're getting there.
Concentration.
This is at a concentration of 2 molar. This was 0.1 molar.
That's it, so that's strong, because it's the same color.
So even though by definition this is a strong acid, what I want to make sure we separate today is not mixing up what that means on the pH scale. The pH scale is simply how much H plus there is. So if you have a very concentrated weak acid, it could have a lot of H plus even though it's at equilibrium. But if I had a same concentration, strong versus weak, which one's going to have a lower pH? The strong one, right? Or it'd be a stronger, that inverse is confusing. Right, so if they're the same concentration, a strong one's going to produce more H plus. But that's what you need to keep in mind, is that concentration is really what plays the role of pH. Izzy?
If you mix the blue and red, would it make a green?
Would it make a yellow?
Stay tuned.
It would make a yellow, right?
Well, no, because it's
Because it becomes
neutral's,
neutral.
neutral's green.
Oh, I thought neutral was
Yeah,
yellow.
our water is bad. That's a bad example.
Oh, I thought.
Okay, so for example, when a problem now says, what is the pH of a 0.04 solution of HClO4? When you know that something is a strong acid because it's on our list, these types of pH questions are very straightforward, because what do strong acids do? Ionize completely, right? So let's write the reaction. So the HClO4
Oh, I found it.
is really,
What's the links that are underneath this table?
oh, did something get disappeared?
Yeah, I feel like this one.
I think it's when you tried to optimize it.
Under what table? That strong acid one? Oh. So with strong acids, we will not use the equilibrium arrow. So you'll never see equilibrium arrows with strong ones because the reaction lies entirely to the right, or the products. Yep. Yeah, it's not, you don't even say it's product favored, it is just product, right? There's no reactant whatsoever. Okay, so this reaction's already on your prop paper. So what I want you to recognize here is it told us, if we think of it like a rice chart, you'll see a rice chart's not really necessary, but this way will give you a good comparison. Okay, how much initially did I have?
0.04.
Good, so this is 0.04, these were at 0. Keep in mind, if I want pH as the end goal, what am I trying to isolate?
H plus.
Yeah, I need to know how much of this there is, right? That's the goal, because that tells me what the pH would be. Well, since it's strong, how much of this is left in the end? None, right? So all of this goes away, which means if this decreases by 0.04, technically this one too, I don't really care about that substance, but you want to fill in your race chart, which means the amount of H plus is the same. So when something is strong, you don't have to do rice charts because whatever you started with is the amount that was created. So to find the pH of this, I would just take the negative log of 0.04.
Basically, anytime you have an else with H plus pH, just negative one.
Yep. Questions on that? Once again, this wasn't necessary, but I wanted to walk through it so you could see why it is just what the problem gave us. Okay, let's look on the reverse side of now our strong bases. So here's our list of our strong bases we're eventually going to memorize. The strong bases are a little easier to memorize because there is a pattern to them. So all of them have OH, right? And the starting substance, if you look at the top of the list, look at the periodic table. I'm going to read this, you look at the periodic table, and you see find the trend. So LiOH, NaOH, KOH, RbOH. So the first ones are just column 1. Then after column 1, you start at calcium and go down. So it's a little bit easier because they're kind of grouped together.
What about B and Mug?
Say that again.
B and Mug.
Oh, yeah, so those smaller ones don't do the full ionization, so they're not strong. Yeah. But what we see here is similar theme, right? Is that when something is strong, it's going to completely dissociate. Yeah, Michael.
Would francium or radium do that?
Theoretically, yes. There's not enough of them like on Earth because they're so radioactive. But yeah, theoretically we'd say they're probably strong bases as well. Good observation. Okay, questions on what makes something a strong acid or strong base at the molecular level? Okay, so let's do one last problem, and then what we'll do is next time we'll then pick up with calculating the pH when something is not strong. Because similar to our acid, so let's look at our base problem here. If it's a base, and it's a strong base, close.
It's a 10 to
So what is that going to tell me about it, Tyler?
It's gonna give me.
That's the pH, it's not the pOH.
Oh, wait, no. No, it'd be the same.
So the question wants to know what is
equals
pH,
negative
right? Do I know how much H plus there is from what's given?
No.
No, but I do know how much.
Oh, H minus.
There you go. So if I can find the pOH by taking the negative log of the original,
Yeah, it's what I'm saying.
028, and that would give me the pOH.
Oh, we're trying to find the pH.
But then to get to pH, you would just 14 minus. I think it's like 1.55.
5.5.
Thanks, Andrew. And so then 14 minus to convert it back. So pretty straightforward still though, but you just have to do a little switch from the pOH side to the H side.
I mean, for some reason, submit my sensitivity.
Oh, good. We're off to a great start. It's day 1, but I'll take it. What kind of day 1?
Day 1 is always like a trick though. It's like,
Are
oh,
you
it's just so easy, and then I say,
It does get more, but if we're building a good base, that's what we're Oh.
We should mix them now.
You want me to mix them?
Yeah.
I agree with you.
This one, this one?
Is it just got purple? That's so boring.
oh wait, base
No, it's hitting
is
the
the base.
I'm gonna run out of space.
Why does it change so that anything in between?
Why did it go green?
Well, it did.
Because I poured too fastly.
What did you add to the
Because if I go one drop past, it switches to acidic, right?
So if it was in slow mo, it would switch green for a second.
There was green. Did you see it? We'll actually do this on another day in slow motion. Well, like not slow motion, but like I'll add it slower so you can like see it.
Can I have the strawberries?
Okay. So your homework tonight here, everybody, is to finish both the pogos if you have. So if you've done both the pogos, you have no new homework. If you didn't get one of them done, then you have an extra day to, it's already late, but you have an extra day without new homework to get it done.
I was very confused.
Nope, nothing from the packet yet.
I don't really know what
Will it count it as late?
You're, no, because you were